Right, so we started off by looking at the basic structure of computers. I think our last slide, or the last thing we looked at, was the impact of computers on society. And we said in our class today, we're going to be looking at the functional units of a computer. So when we talk about a computer's functional units, all we are talking about is the independent parts that make up the computer, or the components, the various parts of the computer or the systems that make up the computer. So if we talk about the functional units, these are basically 5 functionally independent parts of the computer. And from the diagram you see there, we have the input, the output, the memory, the ALU, which is the arithmetic logic unit, and then we also have the control unit, which is part of the processor. Okay, so these are the functional units of the computer. Now, when you take the functional units one by one, the first one being the input unit, it is basically there to accept inputs into the computer or data into the computer. And some examples of this input unit is the keyboard, the mouse, we have the trackball, you have microphones. In some cases, you have some transducers or sensors that are able to pick some inputs and feed into a system. These are all input devices. Then when we talk about the memory is basically where data or information is stored. Data which is yet to be processed can be kept in the memory, or data which has been processed into information can also be kept in the memory. Now, the memory can be classified into primary and secondary. And we have the main memory and then the second memory, like I said, primary and secondary. The main memory would be the memory that is installed within the computer or within the system. The secondary could be an external or a partition drive. It could be a CD, a compact disc. It could be an SSD, etc. Then when we talk about the processor, in this case, because we are looking at the basic structure of a computer, we are looking at it at the basic level where it is basically used for arithmetic operations. Then we'll be talking about the ALU. Now, what the processor or the ALU does is that it is responsible for every arithmetic operation that goes on in the system, say addition, multiplication, division, and all that. Now, the processor is only responsible for processing. It does not keep or store any data. So any data or information that needs to be worked on would normally be picked from the memory into the processor for execution. Then we have the output, which is basically that component of the functional unit or that part of the functional unit that allows an output to be displayed or an output to be given. So in this case, we can talk about the monitor being an example. speakers also being examples, okay? Now, the control unit is responsible for coordinating all activities within the computer. So basically, this is the functional unit and its explanation. So in the next slide, it explains how the functional units work together. So input device accepts some coded information as source program if we are dealing with high-level languages. This is either stored in the memory or immediately used by the processor to perform the desired operations. The program stored in the memory determines the processing steps. Okay. The computer converts one source program to an object program and then finally into a machine language for the computer to understand. If you remember in our previous class, we said that the computer is the language that the computer understands is basically machine language. So in whatever language a program is written in, before the computer would be able to process it or be able to use it, it has to be converted from that level of language to a lower level language called the machine language. So finally, the results are sent to the outside world through the output device. Okay, and all these actions are coordinated by the control unit. So time has been taken to kindly mute yourselves. Time has been taken to explain the various units. So just as I have given the general explanation, this slide goes ahead to explain what the input unit is and has given it some examples. The arithmetic unit as well, or the arithmetic logic unit as well, has been explained here. The output unit. And now let's look at something we term as some basic operational concepts. Okay. So to perform a given task, an appropriate program consisting a list of instructions is stored in the memory. I think we have already established this. Now, these individual instructions are brought from the memory into the processor, which executes the specified operations. One thing you should understand is that for every instruction that is executed by the computer, they consist of two parts. That is the operational code, which we normally call the opcode, and then the operands. So you normally have an instruction, be it a machine instruction, an assembly language instruction, or any of the higher level language instructions would normally have two parts. That is the opcode and the operands. So let's look at this basic instruction and see how such an assembly language instruction can be executed within a computer. So first, this instruction would normally be stored in the memory. So before it is being able to be executed, the instruction will first of all be fetched from the memory into the processor. It will be fetched from the memory into the processor. Now, the operand at location A is fetched and added to the contents of a register. And that register is register 0. And then finally, when the instruction has been executed, the resulting sum is stored within register 0. So basically, this instruction here, add LOCA, RO, the add there is basically the opcode or the operation, which is addition. And then LOCA is just telling us the location of the operand. That is, if they are numbers, what needs to be added together. And then the register is basically a temporary location that would store the results. So this is how, at the basic level, machines would normally execute instructions. And this has been illustrated using a simple assembly language code. Any question? If you have any question, yes, Yabua.
Yeah, please, I can't see on the screen. Oh.
You don't need to see me.
Okay.
Once you can see the screen and you can hear what I'm explaining, you should be fine. Or you want to see my face?
No, sir, please, I'm talking about the screen.
Oh, then it's your internet because others are seeing the screen. Is that not it?
Yes, sir.
Yes, sir.
Yes, sir. But Printer, someone's complaining that they can't join.
It's because they didn't join early.
Okay, sir.
So I am admitting them now. But next time, if it is 4 p.m., make sure it is 4 p.m. Else, after a certain time, I will lock the meeting room and nobody will be able to join again. All right. So can I continue?
Yes,
Okay,
sir.
I see some hands up. Kennedy Adu Jr.
Yeah,
Sir, please, I want to ask a question. We're talking.
Yes, Kennedy.
Okay, sir, please. So you were talking about a language. So I learned you said the art is the opcode where the LOCA is the location, while the RO is the operand.
A register that
The register.
holds
So
the result.
Okay, so please, which language are we talking about? So where is the specific part of the language?
Okay, so I just picked an instruction. So if you see the topic, you realize I'm talking about how an instruction is executed. Just so you understand how execution of an instruction is done within a computer. And in this case, that example of instruction is an assembly language. Were you in my previous class?
Yes, please, sir.
Did you remember we talked about levels of programming languages where we talked about lower level and then high level languages?
Okay, sir, I think I came in late, so maybe I missed that session.
Okay, so what we have two levels of programming languages. We have low level languages and then we have high level languages. So normally the computer at the basic level, the only language the computer understands is what we term as the machine language, okay? Now, the machine
sir.
language is basically a language that is written using or with its instructions written using zeros and ones. But because of the complex nature of writing instructions with zeros and ones, then assembly language was developed. Assembly language is also a low-level language, and that is close to machine language. However, in today's world, we do more high-level language programming than we used to do low-level programming. So today we write instructions or we write programs using high-level languages like C, Java, C++, Python, etc. But before these high-level languages can be executed, or these high-level language programs can be executed, they would have to be translated into a machine language. Okay, so I was just explaining there are concepts you need to understand, like execution of instructions, how the instruction is executed. So this assembly language is just used as an example to explain to you how an instruction is executed. So here, add location A, comma RO. What it means basically is that in location A, there are some operands there. And then we want to add these two operands together and store the results in a register. So this is basically just the explanation of instruction execution. I don't know if you get it now.
Okay,
Yes,
sir,
Kennedy.
so I get it. I get the explanation. Yeah, sir, so I get the explanation now. But what I would like to know is, I learned you said the low-level language is close to machine language. So then,
No,
what is the
I didn't
difference
say
between?
that. I didn't say that.
What is the difference between?
What I said is that the assembly language is closer to a machine language. Machine language is an example of a low-level language. Assembly language is also an example of low-level language. Symbolic languages are also
Okay, sir.
examples of low-level language. So now, what is it that you still don't understand?
Okay, sir. So I get it now. So, sir, what are the differences between the low-level languages and the high-level language? As you said early on, that a low-level language usually uses numbers, while the high-level language has something like Java, C, C++. So what are the differences we can state as a low-level language and a high-level language?
So the low-level languages, example, machine language, uses zeros and ones to write its instructions. Now, it becomes very cumbersome, or it becomes very difficult on a programmer to remember several lines of instructions consisting of zeros and ones. Now, machine languages are also, in some cases, machine dependent, which means that a machine code or a machine language program written on computer A cannot be able to be executed on machine B. Okay? But at the inception of computers, there was no other way apart from to use the machine language or assembly language. However, the difference between the machine language and then the assembly language is that programmers tried to find a way where they could write instructions with more English characters. So if you see the example there, you would realize that you will see a lot of shorthand English. But still, that wasn't enough. And that brought about the development of high-level languages. And now these high-level languages have their syntax mostly in English with rich set of operators, some of them being logical operators, arithmetic operators, and then different usage of alphanumeric characters. So this makes programming easier for the programmer. So if you are looking for the advantage of high-level languages over low-level languages, the major advantage is that it makes programming easier on the programmer. And this is done with the philosophy that any computer system is strong enough to handle, or the hardware is strong enough to handle the software. So the programmer should be able to write their codes using a high-level language, and then because there will always be a compiler, the compiler is what will do the translation from the high-level language into a lower-level language which the computer understands. Kennedy, do I make sense to you?
Yes, please, sir.
All right. Matthias. Matthias, your hand is up. Okay, if he's not ready, let's continue. So, the same instruction can be written in another way. Load the contents of location A into register 1. Add the contents of register 1 together and then display the contents in register 0. So basically what this means is that there are some operands within the memory located in location A. And mind you, the processor has what we call registers that store the information or the data for processing temporarily at the time of processing. So the operands are loaded from the memory into the processor, and that addition is done within registry 1 or register 1, where you have two operands being fetched into. Then when they are added together, their output is stored in register 0. So this is basically an explanation of basic instruction execution, or how instructions are executed. Please, are we okay? Okay. Stephen Appiah, your hand was up. Or your hand is up. Stephen, okay. If you don't have anything,
muted his mic.
If you don't want to say anything, you can put your hand down. Exactly. Okay.
It's like he's speaking, but the mic is muted.
Oh, really? He would have to be able to unmute it himself.
Before he can speak.
Yes. I'm not sure he wanted to speak. I think he wanted to give thumbs up, and then he mistakenly raised his hand. All right, so let's continue. Now, because we've been talking about execution of instructions, we would want to understand the connection between the computer memory and the computer processor. Okay, the computer memory and the computer processor. Now, this image you see here illustrates the connection between the memory of the computer and the processor. When you look at the diagram, you will see that all the arrows that point into the processor and point also into the memory are bidirectional. There are two directions. What this means is that there is a bidirectional communication between the memory and the processor. Now, within the processor, there are several components, or there are several parts within the processor. We have the IR, which stands for the instruction register. We have the PC, which is known as the program counter. Then we have the MAR, which is known as the memory address register. We have the MDR, which is also known as the memory data register. Then we have a couple of registers, that is the number of registers, R0, R1, R3. We have the control unit, and then we have the arithmetic logic unit. Now, during the execution of an instruction, the instruction that is being executed at a particular moment is done using the instruction register. Now, whilst that instruction is being executed with the coordination of the instruction register, the program counter points to the next instruction within the memory that would be fetched and executed. Note that most of the time programs will consist of several instructions. So these instructions will be executed in most instances one after the other. So as an instruction is being executed with the coordination of the instruction register, the program counter points to the next instruction that will be executed. Now, the function of the memory address register is that it keeps the address location within the memory of the instruction that is to be executed. And then the memory data register keeps the address of the data. Then, of course, the control unit controls all the activities within this system. So, as I have explained here, in addition to the ALU and the control circuitry, the processor contains several registers used for several different purposes. Instruction register, it holds the instruction that is currently being executed, and it also generates the timing signals for execution. Now, because there is a connection between the processor and the memory, there is the need to have synchronization, else communication would not be possible. So the instruction register also generates the timing signals that assists or helps synchronization. The program counter, as I explained earlier, is responsible. Is responsible or contains the memory address, whoever it is that is making that noise. Turn your microphone off. It contains the memory address of the next instruction to be executed. And that is fetched from the memory for execution. It also holds, or the memory address register holds the address of the location to be accessed within the memory. And then the memory data register contains the data to be written into or read out of the address location. Now the MAR and then the MDR, or the memory address register and then the memory data register, they help facilitate communication with the memory. So this diagram you see here is what we term, or is the illustration of, or the illustration between the processor and the memory. So you take note of that.
Is there any problem?
Hey, some people are making noise here.
Now, Joseph, you have a question.
No, like the background of some people are making noise.
Don't worry, I have disabled his mic.
Okay.
David.
Sir, we can't see the screen. No.
Oh, then it's from your internet. Because you are supposed to see the screen.
Yes, sir, we are seeing it, sir.
All right. So then, David, check the strength of your internet. All right. Now let's continue. Another concept we would want to establish is a concept called interrupt. Interrupt. Now, if you have used computers, or if you have ever used any computer system, you realize that there are instances where you probably will be performing a certain task. And then when there is a slight glitch, you will get a prompt to tell you that there is a problem, so you can't continue. A typical example will be when you try to create a document on your computer and you don't save the document and you try to close it. You realize that the document prompts you with a pop-up message and says, save or go ahead and close it. Now, in computer systems, we term that as an interrupt. Okay? We term that process or that prompt as an interrupt. So normal execution of the program may be preempted if some device requires urgent servicing. Example, let's take a monitoring device in a computer-controlled industrial environment. Let's say, for instance, in a company like Coca-Cola, where they manufacture drinks or they produce drinks, and then they have a system that fills their bottles. And normally, before the bottles are filled, there is another system that ensures that the bottle is clean. So if an unclean bottle gets there, a prompt will be given that there is a problem. Until that bottle is taken away, it will not be filled. That is an example of an interrupt. Okay? So in order to deal with the situation immediately, the normal execution of the current program may be interrupted, and the device raises an interrupt signal. The processor provides something we call the interrupt service routine. What this does is that it saves the state of processing at that particular time within the memory. And then after the interrupt has been resolved, it will continue. Okay, so this is the concept of what? Interrupt. Please, any question? Any question? All right, if there is no question, then I would continue. Another concept we would want to understand is the bus structure. Bus structure. Let's leave the classroom a little bit. Let's come into our normal daily life. Let's take, for instance, in the morning when you have to go to school. And let's say you live at KNUST and you are coming to the KSTU main campus. We have roads that connect these two places. You can either decide to use the main highway. You can either decide to go through Ascorimampong and get to the Bobine area, the Bobine or the Akwatia line area, and come through Asawase and then enter KSTU. Somebody may also decide that they will go through Ahinsan Estate, go through Atonsu, and pass through Stadium and come to KSTU. Someone may decide that when they get to Afonkwanta, they will go and pass behind KTI. These are all routes that enable movement to KSTU. Similarly, within a computer system, the various connection paths to the several devices within the computer is what we term as what? A bus. Okay. And these are normally lines or wires. These normally will carry data signals, address signals, or control signals. The illustration you see there is basically an illustration of a single bus structure. So if we can have a single bus structure, then it means that we should also have multiple bus structure. So if you look at this illustration here, you have a line where the input is connected into the line or the path, and then the memory is connected into and out of that path. The processor is also connected into and out of the path, and then the output device is also connected out of the path. Now, can anyone suggest or tell us why these arrows are looking the way they are, especially for the memory and the processor? Why do you think that there are bidirectional arrows, David? David, your hand is still up. Oh. If you don't have anything to ask, lower your hand then, or I should do it for you. All right, for you, a blessing.
Please, it's not about the question. I just raised up my hand, but you didn't mind me.
What is it about?
Please, some of my colleagues are requesting to join, but you are not minding them.
Yes, they are late. We've been here for 1 hour. The class is supposed to start at 4 p.m. It's 5 p.m.
So some of them joined, but the network hung up and they are still requesting to join. That's why.
Okay, I have added them now. Even with that, we have only 88 people. Meanwhile, I expect to see about 160 students here, but only 88 people have joined so far. Okay. Yes, Francis Mensah.
So it's about my sister's question that he asked. You know, some phones don't have that Microsoft that you are using. So unless the person download, that is why many people are late on the platform. Even as for me, the time that you send out the link, I download the Microsoft before I sign in, before I can join it. So that's the reason why some people are late. They can't join the. That's why they are late. So please, we beg you for today to allow them to join it. So next time, then if they come late, you won't allow them. It's no problem.
Okay, I hear you. Danso Emmanuel. Emmanuel Danso. Set.
Sir, please, about the question, I think the memory and the processor, they send and receive messages on the bus.
Okay. So exactly, that is the main reason why there is a bidirectional connection in and out of the bus. Because that is the path for communication, there would have to be that bidirectional communication so that they would be able to communicate with each other. But the input device is basically a device that sends input into the system. It doesn't take anything out. That is why there is only one arrow connecting it. And then similarly, the output device only allows some output out of the system. Okay, so you got it right. Now, let's continue. Now, like I said earlier on, there are two types of bar structures. We have the single bar structure and we have the multiple bar structure. Just 1 second, a minute. Now, the single bar structure allows only one transfer at a time. Okay? And designing systems with single bus structure would normally come at a very low cost. And if you need to attach another peripheral or another device to the single bus structure, it would be very flexible to do. And its performance compared to a multiple bus structure would be low. So let's look at the illustration of a multiple bus structure. So the image you see here, you would see a main memory with a bus system or a system bus, and that is connected to a processor. Now you see that that system bus has been bridged to a high-speed bus, and that high-speed bus has also been expanded into another bus. So you see that several peripheral devices can be connected to the various buses that have been created. And now, by so doing, you can have different processes running at the same time without compromising on the performance of the system. So the multiple bus structure allows 2 or more transfer at a time. It also allows concurrency in operation, and its performance is very high. Any question? Any question?
No, sir.
All right. Someone, okay, Nathaniel, are you asking a question or?
Yes, sir. I'm asking a question.
Okay, go ahead.
So the concurrency, can you explain it?
When we say something is concurrent, it means it is occurring at the same time. Two things or two different things are happening at the same time.
Okay, thanks.
That is what we mean by different processes can be running concurrently.
Okay.
All right. Now, to further explain bus structure, let's look at some devices and the kind of buses they are likely to be connected to within a system. So when you take an electromechanical device like the keyboard, this would normally be connected to a slow bus because the keyboard does not need a fast bus. That would be a waste of resource. But when you take a device like the memory or the processing units, they have to be connected to very high buses or high-speed buses within the system. Similarly, something like an optical disk drive needs to be connected to what? A high bus or a high-speed bus. Okay? Now, in some or in most cases, you would find something called the buffer register, which is connected with the bus. Now, what the buffer register does is that it holds data or information which is being carried across the bus during transfer so that we don't lose that information. And the buffer register prevents the high-speed processors from being locked to slow input-output devices during a sequence of what? Data transfer. So this is the concept of bus structures. Any questions so far?
Please, sir, we can't hear you.
Okay, I wasn't speaking actually. I was waiting to see if someone will ask a question. But since there is no question, let's look at performance within computer systems, another concept. Now, for best performance, it is necessary to design the compiler, the machine instruction set, and the hardware in accordance or in a coordinate way. What this means is that systems would normally have compilers because we are using high-level language instructions. So the compilers will aid the translation of these high-level languages into machine instructions, which would be able to communicate with the hardware. Now, how these things are designed determine how fast or how efficient the systems would be. So if we want to measure the performance of a system, one way of doing that is by checking the total time required to execute a program. And that is what we term as the elapsed time. So the elapsed time is one measure of assessing the performance of a system or a computer system. Another thing is the processor time. That is the period in which the processor is active. Is what we term as what? The processor time. And mostly this would depend on the hardware that is used in the execution of the instructions. So these two helps us achieve or measure performance within computers. Now, another way of increasing performance where we try to reduce burden on the processor is processors with something we call cache memory. Now, if you have noticed, take any website for instance. The very first time you visit a certain page of a website, you realize that when it is loading, it takes some time. But if you have visited that website before and you are going back there again another time, you would notice that it does not take that same amount of time to render that website to you. This is because an image of that website you visited earlier has been stored in something we call the cache memory. And this only helps to re-render the page back to you within a shorter period. And that is a way of increasing the performance of computer systems. So cache memories help to increase the performance of computer systems. Please, any question? All right, let's look at another concept, which is called pipelining and superscalar operation. A substantial improvement in performance can also be achieved by overlapping Joseph, how can I help you?
Please, I want to know much about the catch system.
What do you want to know about it, apart from what I have said? What
You
did
said
I say is
when
that,
when you first visit the place, the image of what you have visited already is stored in that catch system.
that wasn't
I
the
want to know
definition
much
of a cache
about
system.
it
A
in
cache
concerning
memory.
with the information that you have stored in there.
Come again. Joseph, you are not clear. Come again so that I can answer your question. What I said was that the cache memory is also a type of memory
What I'm
that is
saying,
used to
the caching.
increase. Huh?
Yes.
So what I said basically is that the cache memory is a memory which is used to assist or help improve performance of a system. And what the cache memory does is that it basically keeps an image of a previous execution so that when that process needs to be undertaken again, there is always an image to re-render or to re-execute that instruction. So I only used that page execution as an example or as an illustration to explain cache memory. Do you understand?
Yes, sir.
Okay. So let's move on. Now, another way of improving performance in computers is with the concept of pipelining and superscalar operations. So here, performance can be achieved by overlapping the execution of successive instructions using a technique called pipelining. Here, what happens is that within the instructions can be written in such a way that within one clock cycle, several instructions will be running in parallel, which would create parallel path. And when this is done, we call it a superscalar operation or execution. Okay, so pipelining is also another way of increasing performance within the computer. Now let's look at what addressing modes are. Like I earlier on explained, I mentioned that normally programs we write for computers today are written using high-level languages, which allows the programmer to write programs in a more easier way. Now, in writing these programs, the different ways in which the location of an operand is specified within an instruction is what we term as an addressing mode. So, some examples of addressing modes are immediate mode, register mode, absolute mode, indirect mode, index mode, relative mode, auto increment mode, auto decrement mode. So, when you get out of this classroom, what I expect you to do is that go and read on all these modes of addressing or all these addressing modes. Try to understand what they mean. Another way of increasing the performance of a computer is instruction sequencing. Now, a computer must have instructions that are capable of performing the following operations. If you are writing a program or a set of instructions, in order to achieve performance, your instruction should be able to allow data transfer between memory and processor register. It should be able to perform either arithmetic or logic operations on data. And there should be a flow and control within the instructions. And there should also be the possibility of transferring data between the input and the output. So these are also ways of improving performance. That is instruction sequencing. Now, the last thing I would want to explain is what we term as the CISC, or the complex instruction set computer, and the RISC, which is the reduced instruction set computer. Now, what these mean is basically a description of computer processor architecture. When we take most computers like the Intel and then the AMD processors, these are based on CISC architecture. Now, the philosophy for this architecture of having complex instruction set is that it is believed that the computer system, the hardware, is always faster than the software. So therefore, if you are writing instructions or if you are building an architecture for the processor should be able to perform powerful executions on powerful instruction sets. But in this case, the instructions are not going to be plenty. It's going to be just a few, but can perform a very powerful function. On the other side, we have the RISC, which is the reduced instruction set computers, or CPUs. Now, these CPUs came into being or came into existence, or they evolved somewhere around the 1980s. And the philosophy behind their evolution is that almost no computer or no one uses complex assembly language or machine language directly, as is used by the CISC architecture. And so, because people use compilers and high-level languages, there was no need to put burden on the hardware. So, in this case, you write simpler instructions, but plenty of them. There is that debate on CISC and RISC, but we are not able to say one is better than the other. It can only be done based on what? Application. So the RISC architecture and then the CISC architecture are all architectures that are useful in computer systems. So this brings us to the end of Unit 1. Any questions? Any questions? Yes, Kennedy.
Okay, sir. So please, I wanted to ask, the CISC and the RICS, has they gotten to do with the performance of the computer or rather the language aspect?
So it is basically, you see, performance of a computer does not depend solely on the architecture. The performance of the computer will depend on processor speed as well, okay? The performance of a computer can also be determined based on what set of instructions it is being executed with. Now, this architecture, that is the CISC or the RISC, the philosophy behind the CISC is that we believe the hardware is powerful. So if we are writing instructions, the instructions to be very few, as in it shouldn't be plenty, but just a set of instruction lines should be able to perform a very complex task because the hardware is capable of carrying that task. Then the RISC also believes that it is only when you are using the lower level languages that you need to build an architecture that needs a strong hardware or that relies on the hardware. But rather, because there is existence of compiler and the fact that you have high-level languages in existence, we should not burden the hardware, but rather we should burden the software and write a lot of codes which can be executed because the compiler will translate them into machine language. Now, however you look at the two, literature is not able to pinpoint that CISC is better than RISC or RISC is better than CISC. However, they can only be compared on application basis. There are times in a certain application, you would want to rely so much on the hardware. And there are in certain cases where you would want to rely so much on the software. So for either of these, you can choose between these architecture. And in fact, the architecture for most Intel and AMD systems is based on the CISC architecture. Some of them even blend the two architectures. So I don't know if I have answered your question, gentlemen.
Yes, please, sir, this answer.
All right.